Okay, good morning. So, this is lecture number 4, and today we are going to do the essentially the basics of the double slit experiment. So, this is in continuation with uh, key ideas in quantum mechanics, and the topics today are the double slit experiment. Maybe we'll have some time to go into quantum measurements and the uncertainty principle. So let's call it lecture 4 and 5 essentially. So, why the double slit experiment? I mean, of course, most of you have already perhaps seen it, but essentially the most beautiful aspects of quantum mechanics can be appreciated via the double slit experiment. Uh, we will also get the glimpses of quantum cryptography. Uh, and essentially, what's the connection between the double slit experiment and quantum cryptography, or what principles of quantum mechanics make quantum cryptography possible? Uh, Also, I would tell you that you can regard the double slit experiment itself as a quantum computer, or quantum computer to be a gigantic double slit like experiment happening. So, so that's essentially the idea. Okay, so how do we set up the double slit experiment? Uh, so let's do an experiment with bullets. So I have a double slit experiment where initially what I do is that I close the bottom slit. I just have one slit open and I have a gun. This is randomly shooting bullets. It's just spraying bullets at random all over. And I have a screen to collect these bullets. So what I do is that I detect the bullets on the screen and make a histogram. Each time the bullet passes, hits, I click it, click it, click it, click it, click it, click it, and I make a histogram. And from that histogram, I make a probability distribution, P1. Any ideas how the probability distribution is going to look like? Yeah, so I'm just going to specify here, bottom slit closed. This is my experiment 1. So, as you can sense, I'll have a probability distribution that looks like some sort of a curve which is peaked at some point, maybe peaked over here. So that's my P1, the probability which I calculated from the histogram of detecting a bullet as a function of this y coordinate. So that was my experiment 1. So what do I do with experiment 2? For my experiment 2, I close the upper slit and I have the same gun. It's a gun spraying bullets at random. And I close the upper slit. This is experiment 2. Upper slit closed. And again I have a screen. To receive my bullets, and as you can guess, once I collect the bullets, click, 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 and I make a histogram and I get the probability distribution, the probability distribution is going to look like, well, there's a sort of a symmetry. It's just going to be another probability distribution P2 peaked at a particular point over here. So this is P1 and P2. So what are the other observations I make about this sort of an experiment? They might look trivial, but that's essentially the idea that, let me put it this way, that our observations, though trivial, should not be taken for granted. So one observation we make is that bullets arrive in lumps. So, for example, there is not a case that I get 0.7 of a bullet or 0.3 fraction of a bullet. Either I get a bullet at a particular point or I don't get a bullet at a particular point. So we don't observe, let's say 0.7 of a bullet. And we get a probability distribution P1 and P2 in each case. So that was my experiment. Now, what happens, my experiment 3 would be, I open both the slits of the double slit experiment. I have a gun. Experiment 3. I have a screen. both slits are open, and well, what do I get? Now I have again bullets spraying randomly, going. I get a probability distribution something like this guy. And I noticed that P was equals to P12 was equals to P1 plus P2 of the previous cases. So I had a, remember P1 was the probability distribution when slit 1 was open. I'll also let me name the slits as slit 1, slit 2, slit 1, slit 2. So the probability distribution what I get is, this was P1 and I had a similar sort of a maybe a black pen, black ink would do justice to it. Or let me just, yes, so this was P12. So P12 was the sum of P1 and P2. Well, which is not very surprising because classically bullets are classical objects, follow Newton's laws, and when you have two alternatives to do a process, you just add up the probabilities. Okay, so that finishes my experiments with the bullet. Now what I'll do is that I'll repeat the same experiment with water waves. I have the similar sort of a setup. I have a double slit experiment. I have a screen, and let me close the screen over here. So I have experiment 4 where I am using water waves, but again the upper slit is open. As usual, the name of the upper slit was slit 1, and I have a source of water waves coming. They pass through the slit, and I get some sort of an, let's say I'm measuring how much water or the intensity of the waves hitting this screen, and how would I measure that? Let's say I have a tiny piece of cork or a wooden plank or something like that over here, and as the water waves hit the surface, this cork goes up and down, and I measure the height of the cork, h, and I know that the intensity of the wave is proportional to the amplitude square or the height squared. So essentially my cork or any sort of a measuring instrument that's measuring the amplitude of this water wave, I calculate the intensity of the wave to be proportional to h squared, uh, where I would just say h is the height of the water wave impinging on the stream. Uh, Very good. So, what are the observations I can make? Well, certainly I have, uh, like I had a probability distribution, I have an intensity distribution over here. I have an intensity distribution. Uh, Again, you can expect this looks exactly like the probability distribution in the previous case. Qualitatively, this is my I1. Also, my observation is that uh, the screen measures a continuum of intensities. You know, this is difference between doing this experiment with bullets as compared to doing this experiment with waves like the water wave. In the case of bullets, I was either getting the whole bullet, I was not getting any bullet at a particular point in the screen. There was not any case where I was getting zero point 0.7 of a bullet or zero point 0.3 of a bullet. But in this particular case, the screen measures a continuum of intensities. So, for example, H can be 0.7 over here. So what do? I repeat the experiment again with the bottom slit open. Uh, I had a screen. Again, I had a source of water waves. Let me call it experiment 5 in our lab. The bottom slit, or what I was calling slit 2. And I again get an intensity pattern which looks like previously I have a sort of this sort of an intensity pattern which I call item over here. Yeah, so this was so far very similar to the case with the bullets. Now, what happens when I open both the slits? So, experiment 6. Both slits open. And I have my water waves. Now they pass through both slits. And when I see the intensity plot, when both slits are open, the combined intensity looks like this. Just make it again. I12, which was not equals to I1 plus I2. and I see this interference pattern. How do we make sense of it? Of course, we know that these are waves, and waves interfere, and these are the interference fringes, the fringe pattern you see over here. And mathematically speaking, it's easy to explain. Uh, I12 is not equals to I1 plus I2. Uh, we explain that, let's say we write this wave as something with a real amplitude 1, and this is the equation of the wave. This was when slit 1 was open, and similarly for slit 2, case of slit 2 open, this was a similar sort of a thing. With some phase factor relative to the previous case. And how do these waves add up? I just sum up over the amplitudes. So essentially, these are the waves at a particular x on the screen. I have, and I have the usual path length. I am hitting at a particular xt on the screen, and I do some, and this is the phase shift, relative phase of h1, the wave 1 with I1 compared to the second wave. And when I add the amplitudes, uh, that's given by h equals to h1 plus h2, and the total intensity at a particular point on the screen is going to be proportional to the square of the amplitude of the resultant wave. And as you can see, that will come out to be, I've expressed it in terms of complex numbers, so the calculation is not very hard. So I get this as the answer. So notice, not only I had I1, I had I2, I had a term, I had an interference term. And this was giving me rise to my sort of a fringe pattern I was seeing. So the message is that waves interfere, which, well, we already knew that, but these two experiments are important to highlight the fundamental difference between our intuition about bullets, or what we call as particles, and waves like the water wave, and a central difference between them, that okay, over here at x or t, I'll have a continuum of intensities, unlike the case of bullet. And also the fact that I see some sort of an interference. So in our final setting, we repeat what we exactly did with electrons. So that gives us no, there is an essential difference. So there was a The fundamental difference over here is that the way we are doing this experiment, I shouldn't call it a difference, but let's be careful as we were careful in the case of a single photon in a Mach center interferometer. Note, in this entire experiment, we will make sure that there is only one electron at a time in the whole experimental setup that hits the screen. Make sure that only one electron at a time hits the screen. So I do again the same thing. I have an electron gun. And I'm spraying bullets. And this is again the familiar pattern of intensity I get. What I do is that I collect, click, 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 click. I collect, let me call it slit 1 open again. Maybe this is experiment number 7 or something like that. So what do I observe? I observe that when I have the upper slit open, I detect the electrons on this screen, and as I collect the electrons hitting on the screen, I again make the histogram, plot the probability distribution. I get a curve exactly like the bullets. It has a peak somewhere, and I get a qualitatively the similar curve. So also, what are the observations I have? I have the same sort of an observation that like bullets, electrons arrive in lumps. So it is not the case that I'm observing 0.7 of an electron or 0.6 of an electron. Either I observe an electron on the screen or I do not observe an electron on the screen. So one electron is completely detected on the screen. I can repeat the similar experiment where I have slit 2 open. I have the screen. I have my electron gun. And as I am firing electrons, I get clicks and I plot the histogram, which looks like P2, which was exactly the similar thing I observed in the case of the bullets. Now I do my final experiment, experiment number 9, experiment 8. Where I open both the slits. Slit 1, slit 2, I have an electron gun. And I am detecting electrons on the screen. So what do I observe in this case? Again, as electrons are hitting there, the electron gun is spreading all over, the electrons are going, and I get click, 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 click. Of course, mind you, make sure the same thing. I only have one electron. We make sure that there's only one electron in this entire experimental setup at a particular point of time. So maybe what you can do is that you start this experiment, and each day you are sending only one electron. Day 1 you get one click, day 2 you get another click, and so on and so forth, making sure that there is only one electron at a time. And then you plot the histogram, and what do you observe? Well, you observe a curve like this, which I would call as P12, and you can immediately see that P12 is not equals to P1 plus P2. Miraculously or very fascinatingly, something which is at the heart of quantum mechanics, the electrons, like bullets, were observed in lumps, or what we call as a particle. But yet, when I open both the slits, I see an interference pattern. So, and not only that, the most essential part of this experiment is that every electron interferes with itself. In fact, if you look at it, someone asked me a question about our experiment with the photon and the Mach center interferometer. Essentially, over there also the idea was the same. It was not that the photon experiment cannot be explained by wave theory, but the beauty is that even a single photon is interfering with itself and acting like a wave. I shouldn't call it a wave because I'll come to that later, but as far as we know, this is what the observation is over here. And if you look closely, observe closely this particular experiment, this defies classical logic. Why do I say so? See, look at this point C on the screen. At the point C, I have a probability P which is less than P1 plus P2. Let me again draw P1 and P2. Let's say I had a P1, I had some sort of a P2. So this was P2, this was P1. And at a point C, I had a probability which was less than P1 plus P2. Now, classically speaking, how is that even possible? It seems like having more alternatives has reduced the probability. I had one slit 1 was open, I had a P1. When the only slit 2 was open, I had a P2. When I have both the slits open, it seems like having more alternatives has reduced the chance of detection at C. How do I make sense of this? So imagine at C, I'll just continue. Imagine at C, point C, a set of electrons have already made up their mind of hitting C. Opening another slit actually decreases the probability. So imagine at C, a set of electrons have made up their mind of hitting C. Opening the other slit actually decreases the probability of hitting C, which is, kind of strange. Also, let's consider this particular point A. Now, at point A, which is at the center of the screen, the probability is more than twice of P1 and P2. We'll do this mathematically in more detail, but hear me out. At point A, at this particular point, maybe I should redraw the figure or something. Let's see. Okay. Yeah. So at point A, at the center of the screen, the probability is more than twice of P1 and P2. So if you look at it, that's also strange, because it seems like as if when I'm closing one of the slits, it is actually reducing the probability from the other slit also. So think about it again. If we assume that the electron has already made up its mind, there's an electron starting from here, it has already made up its mind on what path, what hole to take, and our changing experimental setup, whether I open the other slit, I close the other slit, does not influence its decision. There's no way I can change the mind of the electron. Then, uh, as long as it has decided where it's going to land, then we must add P1 and P2. So, again, writing it, if we assume that the electron has actually made up its mind on what path, which slit to take, and our changing experimental setup, by experimental setup I mean, I open the other slit or not, does not influence its decision, and it is also decides where it lands, well then we must add up P1 and P2. Well, I'm doing this experiment on each day I have a single electron. That single electron makes up its mind. Then it doesn't matter. Then I have to add up the alternatives. Whatever they do, there's no way I can make the electron change its mind. Then there are two alternatives to do the same thing. Let's say reaching this point, then I have to add. Uh, so I have to add the two alternatives. So what essentially are we talking about? Let's look it up slightly more deeply. This is sort of a subtle issue. Let's say I have the same experiment and I have this is the path from the gun to the slit A1 and A2 and towards a point on the screen over here S. So either the electron can take this particular path or this particular path. So what's my proposition? Proposition A. Electron either goes through slit 1 or through slit 2. So assume that the electron can take these two mutually exclusive paths. If it is going this way, it's not going this way. So assume electron can take two mutually exclusive paths. Well then, what is the probability GS? Probability of GS is the probability that the electron starts here and lands up on the screen S. Probability of GS is the probability of GAIS, which essentially means the probability the electron takes this path GA1S plus probability it takes G this path over here. What does it mean? So where are we going wrong? That's what does it mean? See, till now you can't argue this airtight classical knowledge that if the electron is taking two mutually exclusive paths, then you ought to add up the probabilities. This is just the law of probability. You add up the probabilities due to mutually exclusive events. But fundamentally, this is not what I observe, as I've already seen that the probability observed at C is actually less than P1 plus P2. So where are we going wrong, or what is the assumption? What assumption is to be questioned? Well, the assumption over here is that AI has a definite value. So implies that if AI has a definite value, then I have no other way but to add up these things. But let's say what I observe is Well, this implies that AI does not have a definite value. What does it mean? It implies that the electron does not have a unique and definite path. So this is something very subtle. It is not that I do not know the value of A1 or A2. If there exists any A1 and A2, then I have no other alternative but I have to add these two alternatives. So this is, remember we were doing this discussion about fundamental uncertainty because of quantum mechanics. So it is not that I have closed my eyes and I do not know A1 and A2. It is the fact that A1 and A2 do not exist. A1 and A2 do not take definite values, and that's why that's the only way I can explain what I observe in the experiment. So AI does not have a definite value, and the moment AI gets a definite value, let's say in any experiment, then classical logic follows. I have to add up these two probabilities. So this essentially is uh, the essence or the heart and soul of the double slit experiment. Uh, to make sense of the experiment, let's say to make sense, we still need to make sense of the experiment. What the heck is going on? We know that how do we explain my interference fringes, for example. So for that we have our Feynman rules. Uh, we have probability amplitudes, psi1 and psi2. We add up the probability amplitudes, not the probabilities. And the probability Gs would be given by the individual probability amplitude, psi1 plus psi2, where psi1 is associated with the upper slit and psi2 is associated with the path the electron takes from the down slit. We add these guys up. And the probability is given by the modulus squared of the amplitudes, and in addition to P1 and P2, I get these interference terms. And in general, let's say from a point A to a point B, I have multiple paths. Well, I'll associate a probability amplitude or a complex number with each of these paths. And lo and behold, if there are multiple paths, from A to B, so that means I have several alternatives to go from A to B, and all the probability amplitudes add up. And the probability is given by these guys. Remember, we still do not know what is going on here, by the way. Uh, but this is what best fits the experiment. Who the hell knows what's happening in the universe? But this mathematical treatment actually makes sense and it fits the experiment. And in a way, this is a very operational take on quantum theory. We introduce quantum theory or quantum mechanics as a theory of probability. What's the likelihood of an event to occur? What's the likelihood of an event like an electron hitting the screen at a point C to occur? And this mathematical structure of adding the probability amplitudes instead of the probabilities uh, makes sense of those experiments. We'll see this in more detail in the next lecture, but that's the take home message over here. Thank you.